Welcome to AI Paper Slop. Today we are looking at a brand new paper. It's titled MetaSkill-Evolve, Recursive Self-Improvement of LLM Agents via Two-Timescale MetaSkill Evolution.
Quite a mouthful, but yeah,
Yeah.
it's a massive step forward.
Right. This is research coming out of LMU Munich, CUHK, and a few other labs. And, well, we are going to get right into the TLDR for you.
Let's do it.
So if you've been tracking self-improving agents, prior state-of-the-art frameworks like EvoSkill or GPA.
Right, the ones that evolve their task skills based on execution traces.
Exactly. But the critical bottleneck in those older systems is that their improvement mechanism, like the actual logic of how they evolve, is completely hard-coded. It's fixed.
Yeah, it's so limiting.
It really is. So MetaSkill-Evolve removes that bottleneck by taking the improvement pipeline and just, turning it into a learnable markdown file itself.
Which is such an elegant way to do it.
Yeah, and the architecture uses this two-timescale framework. Task skills evolve on a fast loop, while the MetaSkill, the improvement policy, evolves on a slower loop using the exact same 5-agent pipeline just applied to itself.
And they did this using a completely frozen Gemma 4 31B backbone. No extra model training at all.
None. And it achieves these massive gains like pushing held-out test accuracy up by over 23 points on OfficeQA compared to a no-skill baseline.
Which is honestly incredible for a frozen 31B model.
Yeah.
But to really appreciate the mechanics of what they've done here, we need to unpack that foundational rigidity in current self-improving systems you mentioned.
Right, the hard-coded part.
Yeah. The standard for skill-based agents relies on these analyze, propose, evolve pipelines. Like an agent attempts a task, fails, analyzes its own trace, and then rewrites a reusable markdown skill to do better next time.
Makes sense on paper.
Right. But the logic governing that rewrite is entirely static. The agent is optimizing purely for current task utility, which the paper denotes as U of S, the score of the present skill on a validation batch.
U of S.
Yeah. But by only looking at that, these older systems are just completely ignoring meta-productivity, which they call P of M given S.
So meta-productivity, this P of M given S, that's the rate at which a specific branch generates stronger descendants over time, right?
Exactly. It's about the future potential. Because think about it. When an agent hits a recurring error, let's say it keeps misreading a specific type of data table, and its fixed meta process gives it the wrong fix for that error, well, nothing in the loop can revise the underlying diagnosis style.
Right, it's just stuck.
Yeah, the system just keeps applying the same flawed repair logic over and over. It's essentially a padlock on the meta-level logic.
I like to think of it like a factory. It's like a factory that makes, increasingly better widgets, but the factory machinery itself never gets an upgrade.
Oh, that's a perfect analogy, yeah.
So eventually you just hit a manufacturing wall because the tools making the widgets have reached their absolute physical limit.
Exactly. You can only optimize the widgets so much before you need a better lathe.
Hold on, though. I'm stuck on this utility score, the U of S, because if the agent is getting like a 95% on the validation batch right now, why should I care about the meta-productivity?
That's the trap right there.
I mean, isn't a high score the whole point? If U of S is high, it feels like the agent is already doing its job perfectly.
Well, a high-scoring skill today might reside in a branch that has a fundamentally weak improvement policy. Like, it might have just gotten lucky on that specific validation batch.
So it overfit.
Exactly.
Yeah.
It might have overfit to a very narrow type of problem. So if you only select your next iteration based on current utility, you risk investing all your compute into this evolutionary dead end.
So it's a trap. It looks good now, but it can't grow.
Right. But a branch with, say, a moderately performing skill today, but a highly productive meta policy, meaning that the math shows it consistently generates better, more capable children, that is actually a much more promising lineage.
So optimizing P of M given S ensures the search algorithm invests in lineages that, reliably move scores up over time, rather than just chasing a fragile local maximum.
You hit the nail on the head. You aren't just looking for a good answer, you're looking for a reliable engine for generating good answers.
Okay, so knowing that we have to optimize the improvement process itself, let's look at how MetaSkill-Evolve actually pulls this off, because they don't require a totally new model architecture or some impossibly complex outer loop.
No, they kept it surprisingly clean.
Yeah, they define the branch state with this very neat equation, B equals SMH.
Right, so branch state B consists of the task skill S, the meta skill M, and the iteration history H. Everything's just bundled right into that state.
And that metaskill, the M part, is where the system gets really interesting. It's broken down into 5 distinct markdown components that parameterize 5 distinct agents in the pipeline.
Yeah, the 5-agent pipeline is the core of this whole thing.
Let's trace a failure through this to see how it actually works. So first, you have the analyzer, denoted as Sci-I, which, diagnoses the failure. It looks at the trace and identifies where the logic broke down.
Right, it's the diagnostician.
Then the retriever, Sigma, pulls in relevant insights from other branches to inform the fix.
Kind of like pulling up Stack Overflow for past solutions.
Exactly. Then the allocator, Alpha, sets the compute budget. It basically decides how many child variants this branch is allowed to generate in the current iteration.
Which is super important for cost control.
Oh, absolutely. Then the proposer, Pi, actually emits the specific edit proposals for the code. And finally, the evolver, Epsilon, writes those changes to disk and runs a verification step.
And here's the kicker. Because each of those 5 components of the MetaSkill is just a markdown file, literally the exact same file format as the TaskSkill files themselves, the system can use its 2 timescales to recursively improve itself using the same machinery.
It's just markdown all the way down.
Basically, yeah. So on the fast loop, the TaskSkill updates every single iteration to try and solve the immediate problem. But on the slow loop, every H iterations, the system updates the MetaSkill.
By running the exact same pipeline on it.
Exactly. It uses the exact same frozen Gemma 4 pipeline, just pointed at the MetaSkill markdown files instead of the TaskSkill files.
Okay, but wait. If the exact same 5-agent pipeline is analyzing and rewriting its own internal logic, how does it evaluate itself without hallucinating or just spiraling totally out of control?
It's a very real risk with recursive systems.
Right. Because I can easily write a prompt to check if a Python script solved a math problem, but how do you mathematically grade the quality of an evolutionary edit? How does an analyzer even know it made a meta failure?
Yeah, that is the breaking point for most recursive systems. And it's where this paper introduces this brilliant concept of the synthetic meta-failure trace.
Synthetic meta-failure trace, okay.
Because you don't want the MetaSkill reacting to every single noisy failure on the fast loop, right?
Mm-hmm.
If it did, it would suffer from catastrophic forgetting. It would just be thrashing around.
Chasing every little bug.
Exactly. So every H iterations, the system aggregates the tags, the diagnoses, and the actual utility outcomes of the last H descendants.
It bundles them up.
Right. It folds all of that history, along with the running meta productivity score, into a single synthetic trace document. So to the analyzer agent, the synthetic trace looks identically formatted to a standard single failing training example.
Oh, wow. That is an incredibly elegant engineering hack. You don't need a separate, highly complex meta-evaluation prompt architecture at all.
Not at all. A single analyzer prompt cleanly serves both the fast loop and the slow loop.
It just thinks it's debugging a regular task, but the task it happens to be reading is actually like a report card of its own evolutionary performance over the last few cycles.
That's exactly it. So if the trace shows that the last few edits resulted in negative utility gains, the analyzer reads that and might diagnose, well, maybe the proposer has been far too aggressive with his code changes.
Or maybe the retriever isn't pulling conceptually relevant examples.
Right. It then proposes an edit to those specific MetaSkill markdown files, fixing the way the system goes about fixing things. It creates this closed loop of self-correction without ever needing human intervention to tune the prompts.
Okay, so we have a pipeline that can generate theoretically infinite recursive children, and it's constantly rewriting its own rules.
Yes.
But if it's constantly spawning new versions of itself, how do you prevent an absolute explosion of compute costs? You can't just expand every branch.
You can't go bankrupt in an hour.
Right. The system needs a rigorous way to decide which branch to actually dedicate compute to, which brings us to the directed to cyclic graph, the DAG, and the frontier selection math.
This part is crucial. They persist the entire search history as a SQLite DAG.
A SQLite database.
Yeah, and this is critical for state management. When you are running recursive loops, context windows can easily become polluted with failed logic or overlapping edits.
It just gets messy.
Very messy. So by storing the graph in a SQLite database, the system isolates state perfectly. When the algorithm selects a parent node to expand, it queries the database and restores the exact task and meta snapshots from that specific point in time.
So there is absolutely no leakage of bad logic from a failed divergent branch into a promising one.
Zero leakage. Clean slates every time.
Now, the way they pick that next parent is governed by a frontier selection score equation. And the math here is it's eta 1 times u sub v plus eta 2 times p hat sub v plus eta 3 times n sub v.
Right.
And the ablations on this math are fascinating because they show exactly how the system steers itself. Like eta 1 weights the current utility of the node, right?
Yes.
If you ablate that, the system loses its anchor to reality. It just starts chasing volatile meta-productivity estimates on weak parents that aren't actually solving the underlying task at all.
Yeah, that is the standard exploitation term. You need it to anchor the search to actual high-performing skills.
Makes sense.
Then you have eta 2 weighting p hat sub v, which is the estimated meta-productivity. Now, if you remove eta 2, the search gets trapped on plateaued high points.
It's like the local maximum we talked about.
Exactly. The system will keep trying to squeeze marginal gains out of a branch that has already exhausted its potential, completely ignoring branches that might have slightly lower current utility, but much better trajectory quality.
Meaning they are improving at a much faster rate.
Right. And then you have eta 3.
Right. Eta 3 weights n sub v, which is a visitation cooling term. It basically looks at how many times a node has already been selected for expansion.
And if you drop this term entirely, a single moderately good branch basically creates a compute monopoly.
It just hoards all the budget.
It hoards it all and starves the rest of the search tree.
You know, this setup is highly reminiscent of standard reinforcement learning exploration versus exploitation, but with a quality diversity twist.
Oh, totally.
Because by adding that meta-productivity P term, we aren't just placing our bets on the horse that is currently winning the race. We are systematically betting on the horse that is accelerating the fastest.
The accelerating horse, exactly. And the crucial takeaway for anyone designing these architectures is that diversity in this system is a property of the scoring math itself, not some hard-coded structural construct.
Right, they didn't force it.
No. The engineers didn't have to write manual heuristic rules to force the system to keep different lineages alive. The mathematical tension between those three eta terms organically steers the search toward branches that are productive yet underexplored. It balances itself.
So mathematically, letting the system steer its own diversity works beautifully on paper. But, you know, in the messy reality of actual reasoning tasks, does it actually outperform hand-coded logic?
That's the million-dollar question.
Right. Let's look at the benchmark data and the component ablations, because this is where we see the actual return on compute. They tested this framework on OfficeQA, SealQA, and ALFWorld.
And the progression in the empirical results is strictly monotonic across every tested domain.
It just keeps going up.
It does. You see performance go from the no-skill baseline, stepping up to a static hand-authored skill, stepping up again to single-level evolution where only the task skill evolves, and finally peaking significantly higher with the full two-timescale MetaSkill-Evolve architecture.
And the quantitative jumps are massive. On OfficeQA, they saw a plus 23.54-point jump over the no-skill baseline.
Yeah.
On SealQA, it was a plus 16.09 increase. And even on ALFWorld, which is notoriously near its performance ceiling, I mean, the frozen 31B model already hits 92.31% out of the box. The slow loop managed to push it to 94.23%.
That specific ALFWorld result is highly informative, actually.
Why is that?
Because the single-level evolution where the system only evolves the task skill and leaves the improvement policy static provided zero net gain over the raw backbone on that benchmark.
Wait, really? Zero gain from the fast loop alone?
Zero. The entire 1.92-point improvement came exclusively from switching on the MetaSkill adaptation.
Wow.
It demonstrates that even when task skill evolution completely saturates and can't find any more direct improvements, adapting the improvement policy itself can still uncover blind spots and squeeze out further performance.
That is wild. And you know, the ablations completely upend how we usually think about scaling search too, because they systematically turned off each of the 5 MetaSkill agents to see what would happen to the win rate.
Yeah, and every single component matters, but its impact is wildly domain dependent.
Right. Like on OfficeQA, if you remove the allocator, the alpha agent that dynamically controls the per iteration child budget performance plummets by a massive 19.7 points.
It's a tanks.
But on SealQA, removing the propose or the pi agent that actually writes the edits is by far the most damaging. So why is there such a massive split here? What is it about the nature of OfficeQA that makes the allocator the undisputed MVP, while SealQA relies almost entirely on the proposer?
It all comes down to the fundamental geometry of their respective failure landscapes.
Okay, unpack that.
Well, OfficeQA is heavy on grounded reasoning and tabular arithmetic, When the agent fails a task in that domain, it often lands in a deep pocket of related arithmetic errors.
So it's stuck in a math rut.
Exactly.
Yeah.
And a single narrow tweak to the code usually won't get it out of that pocket.
Yeah.
You need an adaptive widening of the search budget, which is exactly what the allocator does.
Oh, I see.
When the allocator detects stagnation in a branch, it dramatically increases the number of child variants generated, essentially fanning out the search tree to find a mathematically viable escape route.
So if you ablate the allocator, you lock the child budget to a static number, and the system just gets permanently trapped in those arithmetic error pockets.
You're just spinning your wheels.
So OfficeQA requires you to cast a wider net when you hit a wall. How does the failure landscape of SealQA differ then?
Well, SealQA is heavily focused on dense reading comprehension and precise information extraction. Escaping a failure in that domain doesn't require trying a dozen different random mathematical approaches. It requires highly precise, conceptually distinct edit content.
So the actual text of the edit matters more than the volume of attempts?
Exactly. The proposer's ability to take in a diversity hint from the synthetic trace and generate a very specific, nuanced rewrite of the extraction logic is what saves the day. Without an evolved proposer, the edits generated are simply too blunt or too repetitive to fix the subtle logic required for those comprehension tasks.
That makes total sense. And this directly leads into the engineering constraints, because knowing which components drive value is important. But if you're building one of these pipelines at your own startup, you have to tune the hyperparameters governing the two-timescale.
Yes, the dreaded hyperparameter sweeps.
Right. Which brings us to the meta update horizon, denoted as H. They swept H across values of 2, 4, and 8. Essentially, they were asking how many fast task skill iterations should happen before you trigger one slow MetaSkill update.
Right.
And if you're building this, you might be tempted to let the fast loop run for, 10 or 20 iterations before incurring the compute cost of updating the MetaSkill. But the data here shows that's a huge mistake.
Yeah, the data strongly indicates that tighter is better. An H of 2, which equates to 6 fast iterations given their specific node expansion setup, was optimal across every single benchmark.
Every single one.
Every one. If you widen the horizon too much, say pushing H to 8, the MetaSkill just goes stale.
Because by the time the slow loop finally updates the improvement policy based on what happened 20 iterations ago, the fast loop has already moved on to totally different types of errors.
Exactly. The broad meta rewrites end up blindly overriding productive recent changes made by the fast loop. It's like a manager coming in to fix a problem from last week that the team already solved.
Oh, that's a great way to put it. And OfficeQA was violently sensitive to this delay, wasn't it? It shed 9.1 points just by moving the horizon from 2 to 8.
Yeah, you're constantly trying to balance stability against reactivity. If you update the MetaSkill every single step, you're chasing noise and the system will thrash. But if you wait too long, your meta policy is fighting the current state of the agent.
So H equals 2 appears to be the sweet spot for aggregating just enough failure signal to find a real pattern without losing temporal relevance to the fast loop.
Exactly.
Speaking of failure signal, there is a fascinating data starvation issue that popped up during the validation ratio sweep on ALFWorld.
Oh, this part is so interesting.
The researchers found that if the baseline agent is already amazing solving, like around 92% of episodes out of the box, a standard 10% validation set just won't contain enough failures to work with.
There's nothing to learn from.
Right. They had to increase the validation split from 10% to 25%, and doing that boosted the evolve skill by over 4 points at a 0.10 train ratio. I'll make sure I'm mapping this correctly. If your agent is already highly capable at a task, it actually can't self-improve because it's snarved to failure.
Yeah.
It fundamentally requires failure in order to evolve.
That is the inherent paradox of self-improvement architectures. Think about it. If you have a small validation split on a task the model already excels at, the execution trace is basically a wall of green check marks.
Just pass, pass, pass.
Right. The analyzer agent sees no failing trajectories to diagnose. And without failures, there are no root cause diagnoses, no edit proposals, and most importantly, no differential utility to calculate that meta-productivity score.
So the whole meta loop breaks down.
The entire slow loop essentially becomes a no-op. It's running the compute, but it's running on empty. You have to actively design your data splits to guarantee the system encounters its own boundaries, or the meta-learning machinery will just idle.
That's a critical practical takeaway for ML engineers deploying these frameworks in production. You can't just feed the system easy wins. You have to engineer adversity and edge cases into the validation set.
The system requires friction to map out the contours of its own limitations. Without friction, the meta policy simply cannot learn how to adapt.
Incredible. So, to wrap this up, MetaSkill-Evolve successfully proves that the improvement policy of an agent-like, the actual logic of how it learns and adapts, can be treated as just another search object within the environment.
It's just another thing to optimize.
Exactly. By perfectly separating what to do from how to improve and representing both as simple, learnable markdown files, they achieved massive performance gains without adding a single parameter to the underlying Gemma model.
It fundamentally reframes how we should think about agent architecture moving forward. I mean, we spent an immense amount of time handcrafting prompts and rigid logic flows when we could be building pipelines that dynamically engineer their own logic based on evolutionary pressure and synthetic feedback.
Which leaves us with a highly provocative final thought for you. This paper successfully runs a bounded one-level recursion. A 5-agent pipeline rewrites the markdown styles that govern the 5-agent pipeline. But what happens if this logic is extended further down the stack?
Oh boy.
If an agent can rewrite its own meta skills to improve how it codes, could a future iteration of the system rewrite the actual neural architecture? Or write new weight-updating algorithms for the backbone model itself?
That's the dream or the nightmare, depending on who you ask.
Right. Are we looking at the early markdown-based blueprints of a truly recursive Gödel machine? Definitely something for you to ponder as you look at your own hard-coded pipelines today. Keep reading, keep experimenting, and we'll catch you next time on AI Paper Slot.